what we have here geometrically can be represented by this picture. We've got the graph of f of x in blue here, and we've got a graph of g of x up here, also in blue, between limits a and b. The integral of f of x is represented by the shaded area, the area that's shaded in red underneath the graph of f of x, and that represents the integral from a to b of f of x dx. The integral of g of x dx has been shaded in purple. It's written in purple and it's shaded in purple. Notice the shading goes all the way from the g of x function down to the x-axis and overlaps the red shading of the f of x integral. Now, the difference, integral g of x dx minus integral f of x dx, is just the difference in the areas beneath the g of x graph and the area beneath the f of x graph. Since the area under the g of x graph includes all the area under the f of x graph, the difference of the two integrals is just going to be the integral of this strip in between, which I've shaded in green, between the f of x and g of x function. And we say that that's the integral from a to b of g of x dx minus the integral from a to b of f of x dx. That is, this green shaded area represents the difference of the two integrals, which we've of course proved is equal to the integral of the difference of the two functions. Now, by contrast, let's look at what we might mean by the integral of g of x minus f of x. Here we have a similar picture. We've got the g of x function and the f of x function. For any x, g of x minus f of x is just the displacement from the f of x to the g of x graph. In this case, it's always positive, so we're going to represent a selected number of these g of x minus f of x quantities by vertical arrows going from the f of x to the g of x graph. Now, you recall a minute ago that we saw that the integral of g of x minus f of x is just the area between here and here. Another image is we can take these arrows and put them down here, and when we do, if we completely match the arrows with the arrows here, and if we do all possible arrows, that's impossible to do, of course, because there's an infinite number of them, but if we could, we would get a graph of the g of x minus f of x function. So that when we integrate g of x minus f of x, we're really talking about the area under this curve that's obtained by taking the differences between these two functions. And the theorem says that this area is indeed the same as this area. And that's a very significant and very important theorem. Again, it might seem fairly obvious, and if you think about what happens on each tiny interval between a and b, it actually does become obvious. So, if we look at the overview of this picture, we see that here we've more or less proved, again, this is not a completely rigorous proof. A completely rigorous proof would involve the Riemann sums and very rigorous treatment of the limiting process, but we've got a pretty good idea how the proof goes, where we show that the integral from a to b of the difference of the two functions is the difference of the two integrals. Then here we have a picture of what the difference of the two integrals means, and down here we have a picture of what the integral of the difference means in terms of this picture. Okay? And these arrows, of course, indicate this. This arrow indicates that this is this, which is this, and this is represented by this picture giving us this picture.